Okay, I do have the exams done. I'll release the scores after class, and then I'll put the answer key on. The answer key's not online, so I'll have to put that online. And then you can kind of see where you're at. Midterm grades are due on Wednesday, so I'll be putting those in sometime today as well, from where you're at. If you have any questions, look at the answer key first or try and figure out what you did wrong. And then if you need be, you can always come and ask, but try and see what you missed first, because that way you'll help you remember it. Okay, so where were we at? A week ago, 2 weeks ago. 2 weeks ago. That was a long time. So we talked about the idea that activating groups and deactivating groups direct either to the orthopara or the meta position, and the idea that halogens deactivate, but they're also orthopara directors. So I went through, most of the slides here are that what I did in class, because I just decided to go through them in class as opposed to put these up, because then nobody would have taken notes or anything. So these are all orthopara directors, halogens are orthopara directors, and then all the deactivating groups direct meta. Okay, so that's where we were at, and we went through the mechanisms, the mechanism, and the key part of the mechanism was, so just to go back, activating groups direct the electrophile to add ortho and para. And the deactivating group then directs the electrophile to go meta to it. Okay, now the group already on the ring is directing. Okay, that'll become important today. And then halogens, while they're deactivating, they direct to the ortho and para positions. And the reason why, because remember they had a lone pair. And so these were just simply the notes that I went through step by step. And the critical part being that whenever you had a plus charge next to that substituent, if the plus charge could somehow be stabilized, it would be an orthopara director. And one of the ways it could be stabilized is by that group having a lone pair to be able to donate it to form that fourth resonance structure. Okay, so if that happened, then we had an orthopara director. Because when you add a group meta, the plus charge is never next to the original group. So it was always wherever the positive charge was next to the group. If the group stabilized it, it was orthopara. If the group wasn't stabilized or destabilized, then it was meta. And so that's what we saw. So there are all 9 of the resonance structures for adding to the alkyl substituted, where we said that we had, for the first one, we had 2 secondary carbocations and a tertiary, versus when it added meta, we had just 3 secondaries. So the tertiary was able to, this alkyl group right here was able to stabilize that plus charge when the plus charge was next to it. But when we have a deactivating group, if you put that plus charge next to the deactivating group, then what happens? It ends up not stabilizing it. So then we end up with essentially only 2 resonance structures. And in that case, 2 resonance structures is not more than 3 for meta. Normally the meta had 3, that wasn't enough. But in deactivating groups, 3 is more than 2. And so deactivating groups, then the meta was the most stable intermediate. So electrophilic aromatic substitution went by the most stable intermediate. That's how it worked. Right? So that's what all this stuff would have been. And so here's a complete list of ortho-para directors and meta directors. And what you can see is that our generic groupings, like with an X with a lone pair directly attached to the ring, fits most of the ortho-para directors on there. Down here, these are all X double bond Y groups, and those fit most of the deactivating groups. Now, there are some extras on here. I'm just going to hold you accountable for the first 10, the ones that were on that one. Okay. So that's where we were at 2 weeks ago. So now so we should do some reactions here. We're not ready for di-substituted ones yet, right? We're ready for mono-substituted. So let's do some mono-substituted rings. Okay, so I'll take my benzene ring and I will add, what's a good group to add to it at this point? So we take nitrobenzene and we add methyl chloride with aluminum trichloride. And so the question would be, what's the final product of that reaction? Or what's the final products? So if it's ortho-para, there's going to be 2 products. If there's meta, there's just going to be 1. So there are the 2 choices. There's the 2 choices. Either it's going to be group A or group B. Now, if you're like, where did the methyl group come from? It's been a long 2 weeks. Actually, it's only been a long week. Right. That's the first thing I need to do. Right? If I'm writing the products of these reactions, the first thing I need to do is to say, okay, what electrophile is generated from that set of reagents? And that would be the CH3 plus, which I'll put in quotes, right? Since it's not really a CH3 plus. All right, so we got an answer? A or B? That's your choice. All right, I got 14 B's. That can't be right. I have 3 A's and 14 B's. There's more than 17 people here. Okay, I got 15 and 2. There's still more than 15 and 3. There's still more than 18 people here. Okay, but B is the correct answer. Now, I think I know what those of you that said A were doing, because we always have to kind of deal with this. We always kind of have to deal with this at the beginning. So, okay. Now, if you put product A down, and you thought that well, anybody want to give me a reason for A? It's the first day back. I'm not gonna humiliate you. No one? Well, here's what sometimes happens. What sometimes happens is that people will put down product A because they said, but CH3 plus is what kind of group? An alkyl group is what kind of director? It's an orthopara director, right? So that means it must go orthopara. So if you didn't think that way, that's good. But sometimes people think that way. They'll look at that group and they'll say, it's going to self-direct. No. The group that's on the ring is the directing group. And so you don't want to confuse the group that's being added with the group that's already on the ring. This is the directing group, and so it says direct the group to the meta position. And there's 2 meta positions, right? But they would give the same product. So it's the nitro group that tells the methyl group where to go, not vice versa. So the methyl group is not self-directing. The nitro group says this is where the methyl group should go. Okay. Let's try another one. Okay. So there are your 2 choices. Again, remembering that Br2 with FeBr3 gives you Br plus. So where should that go? Which one would be the correct set of answers? A or B? Okay, I've got 15 to 5 with 1 D. There's no D. But 15 A's. 15 A's and 5 B's. So are you all correct? Well, exactly. So the nitrogen, when the nitrogen is attached to the ring, that's an orthopara-director. If I reverse this molecule and attach the carbonyl to the ring, it would have been a meta-director. So this is correct. A is the correct answer for that one. Okay. So my steps are, first thing I need to know is I need to know what's my electrophile. So I can go back to all the electrophiles that we've learned. Friedel-Crafts alkylation, Friedel-Crafts acylation, bromination, chlorination, sulfonation, all of those. Okay. And so you have to remember those, including the ones that automatically rearrange. Right? But then it's the group on the ring that tells that electrophile where to go. So you need to know whether that group is orthopara-directing or meta-directing. Vinny? Yep, it is.
And this was ortho-para because the way it was organized
because the nitrogen that has the lone pair on it is attached directly to the ring.
So what about like this whole group?
The rest of the group doesn't matter. It's the fact that the nitrogen is attached to the ring. That's what makes it active. That's what makes it activating. That makes it orthopara-directing. If I would have reversed the molecule and I started with this one, that would be deactivating meta. Because now what's attached directly to the ring? The carbonyl.
Is there like another one where we would get like that maybe mixed up, like, or is it just always?
This one. So those two molecules, which one's the orthopara-director? The one on the left? And the one on the right's? So it's meta. Those sometimes people get confused about. Or might as well do this one. What if I attached a ring to both sides and then said, bless you, I'm going to add Br2 FeBr3 to that. Which ring do you think it's the Br2 is going to add to, A or B? How about cards? Which ring do you think the Br plus is going to add to? Ring A or ring B? Or both? I've got 16 A's, 4 B's, and 4 C's. Why did anybody say ring A? Christian.
I was just thinking that, like, if you think of O as an activating group, you have the resonance structures.
So ring A is attached to O, and the O is activating. What about ring B? It's attached to the carbonyl, which is deactivating. So which one of those two rings has the greatest amount of electron density to react with the E+? I had to stop there and think, because what are we reacting it with? We're reacting it with an E+, so if I want to activate the ring, what do I need to do? Push electron density into it, right? So which one of those two rings has the greatest amount of electron density? A. So that's where the electrophile is going to add. And then how's the electrophile going to add? Ortho and para. So the Br plus would add there and there. So we would get two products. Okay. So those are the kind of carbonyls can be an issue depending on whether there's an O or an N or the carbonyl part directly attached to the ring. Brian?
Kind of get a thermodynamic product from that if you heated it and then it would add P.
If you give it more energy, you could probably increase the amount of B relative to A. I think that's possible, but there's only so far you could push it. I mean, I think the best you could do is push it 50-50. And what you're doing is, because the intermediate, it's really talking about transition state energy, that you're applying more and more energy so it goes over each barrier equally well. So yeah, I guess you could probably push it to be 50-50. But I don't know what it would be to start with. That would be an interesting thing to look at and see where did it, which ring got reacted. And that would not be an easy problem to solve spectroscopically. That's going to require to know if I took a methyl group and add the methyl group to know which ring the methyl group added to, that's going to take my whole toolkit of NMR to find that out. So that's not going to be easy. Sarah?
Anytime an electrophile has the opportunity to add an activating and a deactivating ring, is it always going to add to the activating?
Yeah. Because it's going to add to the ring that's the most electron rich. And that's the activated ring.
Does that have anything to do with resonance stability too, or not really?
Maybe a little bit in terms of because it's the resonance. After it adds, it's the resonance hybrid, I guess, of that carbocation. And so if it adds to A, that intermediate's going to be more stable than adding to B. All right, so that's adding to one group. Piece of cake. Now adding to two groups. Still should be relatively straightforward. So let's just think about this problem. Let's go all the way back to the beginning. Okay, so bless you. We know we're going to add a Br plus here, right? We know we're going to add a Br plus to that ring. So where's it going to add? Okay. So we can apply these two individually. I could say, how about this? Here's my amine group. It should add ortho and para to it. Now it cannot add over here because there's already a group.
I thought I would see kind of similar thing, but you want to think about it this way, because if it adds ortho and para to the nitrogen group, it's also meta to the COOH.
So let's do the COOH and see where it points. So it's going to point for this one. It's going to point meta to the COOH group, right? Where'd my drawings go? Which are there, right? So in this case, they point to the same direction. So that means that the Br plus is going to add to those two positions. So I'm going to go ahead and write both of my structure, both of my original groups. I'm going to add my Br there. I'm going to add my Br here. And then so there's my two products.
And that's based off of the nitrogen.
That's based, the nitrogen points here and here, and the COOH points here and here. So in this case, the groups point the same directions. They're not fighting each other. And that makes sense. If they're not going to fight each other, and they're both pointing in the same direction, that's where the product's going to go. That's where the electrophile is going to go. Okay, so that one's easy. What's not going to be easy? Well, how about I take my NH2 group, and instead of my COOH group being ortho to it, let's make it meta. So now let's take that molecule. Because now, what's going to happen? Where's the nitrogen going to point? Ortho and para to itself, right? So the nitrogen's going to point here, here, and here. And where's the COOH group going to point? Meta. Which is there because there's already an NH2 at the other meta position. So who wins? Nitrogen because it's stronger, but what does stronger mean? Nitrogen is more activating. So it's a stronger activating group. So nitrogen wins, which is exactly the case. Now in this case you might say, oh well, nitrogen wins because it's activating and COOH is deactivating. Yeah. So if I have two activating groups fighting each other, which one wins? Stronger activating. If I have two deactivating groups, which one wins? The less deactivating. Right? So that's the way it works. And we did this. I did this for probably a good 15 years. Said, hey, they're pointing in the same direction, and hey, now they're pointing in opposite directions, so which one wins? But do I even need to worry about the group that's not the most activating? So the group that's on the ring that is the most activating, it's directing. If the other group directs in the same position, great. If it doesn't, it loses. So all we have to do is worry about what group is the most activating.
So now the next question is, what if they're both the same? So what if they're both like moderately activating and moderately deactivating?
Well, that wasn't going to be my next question, but we can deal with it. We can deal with it. But what I'm really concerned about here, at least initially, is, so, okay, the one that's the most activating wins, and that's going to beat the director.
What did you mean when you said if they're going in the same direction?
That's what happened here.
I didn't get what was going on there.
So the COOH is pointing meta to itself, and the NH2 is pointing ortho and para to itself. And it turns out that they're pointing to the same positions. That's what I meant by they're not fighting each other.
Relationship right there.
Exactly. The COOH has to direct meta. The NH2 has to direct ortho-para. If it happens that they both point to the same position, it doesn't matter. But if they don't point to the same position, then the group that's most activating wins. Sarah?
So if you're adding it based on the NH2 and there's two possible ortho positions, does that mean there's three products? Because they're not the same.
There's three possible positions, but actually in this there's only two possible products here, because I need to add one more thing. Okay. So you're right, it's pointing to three different positions, all of which give different products.
Right.
But here's the problem. The problem is we never add in between ortho or between meta groups. When groups are meta to each other, we never add in between. And you might say, well, never? Yeah, never. Because the problem there is that there's not enough room for any electrophile to stick itself to come in and add to this carbon right here. There's just not enough room. And you could say, well, these things have to be small. No. A methyl group is huge on this ring. And so even a methyl group is going to have a very difficult time adding. You can say, well, what about a bromine? A bromine is the size of a methyl group. So you never add in between meta substituents. So in this case, if I was to add a Br plus to that molecule, the two products that I would get would have the COOH here, the NH2 there, would have a Br there, and then the other product would be NH2 there, Br there, and COOH there. Because I don't add in between. Does that make sense to everybody? So those are the basic rules. The group on the ring that's the most activating is going to do the direction, and you cannot add in between groups. So here's my table of 10. Of 10 things. Only 9 of them are relevant because this hydrogen, that's always the baseline. So what I need to do is I need to rewrite this table like that. I need to go from number 1 to number 10. Because that then gives me the groups in their most activating order. So whichever group is the highest on this list wins. So what does that mean for you? You've got to learn these groups. And how am I going to help you do that? By giving you an in-class quiz on Wednesday where I'm going to give you this table from 1 to 10, and you're going to have to tell me what group is number 1, what group's number 2, tell me whether it's activating or deactivating, and then tell me whether it's an ortho-meta or a ortho-para or a meta-director. So I'll just make a chart, and you'll fill it out. Okay. Because you need to know that. So we might as well learn it now. The thing here is the hydrogen. That's the baseline. So that's going to be empty, right? Because the hydrogen isn't activating or deactivating, and it's not ortho, meta, or para directing. Okay. Right. Any questions? Does that kind of make sense? So we can apply this to anything. Here's another one. So what's my electrophile here? NO. My electrophile is NO2 plus. Where is my NO2 plus going to add? And I got two positions. A and B, because A and B, whether it's on the A right or A left, same gives me the same product. So where's my NO2 plus going to add? Is it going to add to A? Or is it going to add to B? Cards. Okay, I got 16 A's and 4 B's. Which of those two is more activating? OCH3. And it's what kind of director? Ortho, so it's going to direct the NO2 to that position, and that's going to be the final product. So honestly, this isn't as complicated as it might seem. If you know what electrophile you're generating, if you know your groups from number 1 to number 10. And if you remember, never add in between groups. Okay. Everybody okay? Again, I'm not supposed to ask that because nobody knows what that means. Should ask for a 1-minute essay on what you think you've learned. Maybe we'll do that one of these days, but not today. Okay? So we can do this all day. So now what we need to think about is this. We need to think about, if I have a benzene ring and I want to make meta-ethyl nitrobenzene out of it, What should I do? How do I make that product from benzene? Well, first let's just talk strategies. How do I get the ethyl group on the ring? How do I put the ethyl group on the ring? What reagents? Okay, so ethyl chloride, AlCl3 or FeCl3, either one. So that's going to put the ethyl group on the ring. How do I get the NO2 group on the ring? HNO3 with H2SO4. Okay. We're just purely talking strategies here. I need to have a way to put each group on the ring. So I've got these two because these are relatively straightforward. What comes first? What do you want to put on first? NO2? We all in agreement with that? Does it matter? Yes, it does matter. In this case, matters a lot. So first we'll react with HNO3. That's right. HNO3, H2SO4, and then we'll put the ethyl chloride, aluminum trichloride on. Now, why is that important? Well, because what's the HNO3 going to do? That's going to put the NO2 group on the ring. I always like to put the groups where they're at in my final product. Helps me keep them straight. And then that NO2 group is what kind of director? It's a meta director, so that now if I add the ethyl chloride, aluminum trichloride, the ethyl group is going to be directed to the meta position to the NO2. If I reverse the conditions, what would I get? I get ortho and para. Okay. And these are more interesting problems. Right? It's more interesting when you've got to tell me what reagents you need in order to make the molecule. Okay. So then we go to something like this. How do you put an SO3H group on the ring? H2SO4 and SO3. That one must not be at the top of everybody's list. Should get there. How do I put a COOH group on the ring?
And then use potassium.
That was awfully quick. Usually we sit around and look at each other awkwardly for a good 5 minutes before somebody comes up with that, but that's good. So you want to do this. You want to take your benzene ring, you want to add methyl chloride, aluminum trichloride, Friedel-Crafts alkylation. I'll put something small on. And then you want to react that with KMNO4. Because you're going to alkylate the benzene ring, alkylate the alkyl group to make a benzoic acid. Everybody like that? That's good. Because originally it was going to be like, wait, COOH, we don't have a one-step reaction. No, we don't. So that means we need to combine some reactions together. And here's one. Put an alkyl group on the ring. What alkyl group? It doesn't matter because it's going to become a COOH group. So let's just put a small methyl group on. How about another one? There is another. I'll give you a hint. Grignard. What if I take my benzene ring and I brominate it with FeBr3 to put my bromine on the ring? How do I make that a Grignard? Just magnesium metal. So now I've got my Grignard. What do I add to the Grignard to make a carboxylic acid? I heard something. It's in the Grignard reagents. So remember, CO2, the minus comes in, adds to the carbon, then one of the oxygens becomes an O minus. So there's two methods right there of adding CO2 to a ring. So what we have to do now is we have to think about the steps and what order the steps should go in order to get those two, the SO3H and the COOH, meta to each other. So for instance, I wouldn't put a methyl group on and then put the SO3H group on because the methyl group would direct orthopara. So if I want to, I could put the methyl group on, convert it to COOH, and then add the sulfur trioxide, sulfuric acid. Okay. But that's what we need to know. We just don't know enough reactions right now to add the groups to the rings that we would like to. So we need more of those reactions.
Before you close out, could you go back to the slide? No, not to the slide where you were in the list of the activating stuff. And you said the hydrogen was the baseline. When you say the baseline, as far as speed and
it's everything above reacts faster, everything below reacts slower. Yeah, kind of, you can think of it that way. Okay? All right, so what are we going to do on Wednesday?
Have a quiz.
Yeah, that's true. We're going to start with a quiz, and then we will also, I'm going to lecture on adding more groups to the benzene ring.
Is it a live lecture?
To the what?
Live lecture?
Yeah, it'll be live. So no quiz. So no online quiz? No online quiz.
that's what I wanted to copy it. I know I have it, but it's
Well, this is in the Canvas page. You can just download it. All right. Come get your exams. Tom.
Sir? Both having back problems.
No, I missed the step on the administration building, and all my weight came down on one ankle. It wasn't good. I don't bounce anymore, and that was about all the weight.
Do you have a brace on?
No.
I think you should put a first
Yeah, I'm okay.
Diane.
Thank you. Ellie. Maddie. John. Brian. Rhea. Kyle. Melissa. Anita. Kitty. I think Kitty's here. She's probably still in Japan. Hey, John. Melissa. Lisa. Carolyn. Erica. Aaron. Madison. Haley. Vinny. May. Kareem. Sam. Kevin. Paige. Sarah.
Thank you.
Shia. Kate. Christian. Bob. Thank you.